All right. So now what we're discussing is a slightly more interesting example for convergence almost surely. So we'll see an example where where you have a sequence of random variables which converges almost surely not to a point, but maybe to some other random variable. Okay, and let me define the following. So x1, let us say, is uniformly distributed between 0 and 1. Okay, and I'll define, let's say, x. So for n equal to 2, 3, and so on. So xn is, let me say, 1 plus 1 by n times x1. Okay.
Okay, sir.
Right. So all of these random variables are not independent, right? They're not identically distributed, correct? But then it's still it's a non-trivial sequence of random variables. All right. So is this problem clear?
Yes, sir. Like
Okay.
only x1 is the independent.
Correct. Correct.
All are
So basically, all the source of randomness is in x1.
yes, sir.
Okay. Or yeah. So I can make it even more slightly complicated, but let's keep it a little simple for now. Okay. Or yeah. So let's make it maybe a little more complicated. So I will define xn as 1 plus 1 by n yn times xn, where the
Xn or x1,
yn's,
sir.
sorry, x1, where yn is uniformly distributed in 0, 1 IID. Okay, so all the yi's are IID and they're uniformly distributed in 0, 1.
Yes, sir.
Okay. So basically this is x1 plus x1 yn divided by n. Okay. So now let's look at the event an which we are interested in. So what is an? So or whatever am. So the event here is that xn minus x is less than or equal to epsilon for all n greater than or equal to n. Okay, so am. So in this case, I'll take x as x1. So I want to know whether the sequence of random variables xn converges to x1 almost surely or not. Okay.
Okay. So
So
here x1 means like again an interval.
so x1 is a random variable, right? So
Like if you are again
so a random variable is basically a function, right? So so think of it as so you have a sequence of random variables which and corresponding to that you have joint distributions for sequences of random variables, right? They're not independent.
yes.
Correct. So it's not really an interval. Right? And that is a difference between convergence of sequences of numbers and convergence of sequences of random variables. Right? So the way to think about it is in terms of events. Right? You want to know whether some sequence of events, so you want to know what certain sequences of events converges to, or it doesn't converge at all. So in this case, the sequence of events that we are interested in is am, which is that xn minus x is less than or equal to epsilon for all n greater than or equal to m, right? So for each m, this event is well defined, right?
Yes, sir.
right? And you want to know whether this sequence of events, so what is the probability of this sequence of events? Does it converge to 0? Does it converge to 1? Or something in between,
Yes.
right? So now in this case, what is xn minus x equal to? So it's basically equal to 1 over n times x1 yn, right?
Yes, sir.
Equal to epsilon for all n greater than or equal to n, right? So you know that if for m greater than or equal to, let's say 1 over epsilon, this always holds. Do you agree?
Yeah.
So
Sorry, sir.
if, sorry?
I did not get this.
Okay. So this is a sequence of events, right?
Yes, sir.
Correct. So we want, what do we want to find? We want to know what is the probability of AM. And we want, and basically if it converges almost surely, then the limit as m tends to infinity, probability of AM should be equal to 1. Okay. We want to know if this happens or not.
Yes, sir.
Correct? And how do we find out? So now we know what AM is. We don't really care about AM for small m. All we want to know is what AM behaves like for large enough m.
Yes, sir.
Correct? So I'm going to take a guess. Okay, I look at this. So just look at this sequence of events. What do you guess? Do you think that this event will surely happen for large enough m, or do you think it won't happen for large enough m?
Happen.
It will happen, right? Because x1 and yn,
Less than 1.
they're both less than or equal to 1, and you have a 1 over n sitting over here. So definitely if n is large enough, then this quantity, no matter what x1 is, no matter what yn is, what the realization of x1 is and what the realization of yn is, this quantity will definitely be less than or equal to epsilon. In fact, if m is greater than or equal to 1 over epsilon, or if n is greater than or equal to 1 over epsilon, then this quantity will definitely be, this condition will definitely be satisfied. Correct?
Uh,
So if n is greater than or equal to
yes, sir.
1 over
Yes, sir.
epsilon, then definitely the left hand side LHS is mod epsilon times x1 yn, which is less than or equal to epsilon.
Epsilon.
So that is definitely satisfied.
Yes, sir.
So you know that for every epsilon greater than 0, this limit as probability. So you look at the sequence of events AM. So if you look at probability of AM, then you have something non-zero, something non-zero, something non-zero, or something less than 1, and so on. But after m greater than or equal to 1 over epsilon, then the probability of AM will definitely be 1.
Yes.
All right?
Sir,
Yes.
which means for every x1 yn we can find a m for satisfying this condition.
No. So note that x1 and yn are defined, they're fixed, they're given by the problem itself, right? And x1 and yn are random variables. Correct? They're random variables. So one sequence of realizations could be different. So x1 could be 0.1, y1. So x1 could be 0.1. Okay. So let us look at what this sequence looks like. So what a particular realization would look like.
Sir, how did you say that if m greater than equal to 1 by epsilon, then it can satisfy that condition?
So I'm saying this because no matter what the realization of x1 and yn is, I know that x1 is always less than or equal to 1 and yn is less than or equal to 1 because they're uniform random variables, right? They're uniform 0, 1 random variables. So the product x1 yn, it can never be greater than or equal to 1, right?
Yes, sir. Yes.
Right? So that is all that I'm saying. So this happens with probability 1, this particular event. Right? So if you look at the sequence of random variables, it could behave weirdly. It doesn't matter. So we have, yeah. So this is how I defined xn. Maybe x1 is 0.4, let us say. X2 could be 0.4 plus 0.4. Maybe y1 is 0.9, or maybe y1 is 0.1, right, divided by 2. So this would be 0.4 plus 0.02, so 0.42. This is x1, this is x2. Maybe x3 is, so x1 plus x1 into y3. So maybe y3 is, maybe one realization of y3 is 0.3 divided by 2. So this, sorry, divided by 3. So that would be 0.44 and so on, right? So one way to look at this, or one way to understand this better, is to just maybe pull up Python or your favorite programming language, and then see what the sequence will behave like, right? So how would you do it? So suppose I want to simulate this particular sequence of random variables, okay, and so I want to know what this sequence of random variables will behave like. Just try to generate these random variables and see what will happen. Or just write a short program using Python or MATLAB or C or whatever your favorite programming language is, and try to simulate this. So how would you simulate it? You first generate x1, right? You first generate x1. Maybe you use the rand function, uniform 0, 1, and then for I equal to 2 to maybe some large number, you just generate. So xn is basically going to be equal to x1 plus 1 over n times x1 into yn. So it'll just be rand of between 0, 1, whatever function it is to generate uniform random numbers in the programming language of your choice, right? So this would generate the sequence x1, x2 up to x capital N, and see how this behaves. So every time you run the program, you're going to get a different sequence of numbers, right? So print x1 up to xn, and also try printing, so try to find am, right? Or one way to look at it is also print x1 minus x1, x2 minus x1, x3 minus x1, and so on. All right, so print these two things and see what will happen. So this can be any sequence, but this sequence will definitely be so for large enough n, this will all be close to 0. All right. So try to run this experiment and see what happens. All right. So do this experiment for and try to run a similar experiment for the other examples as well. Right? So there are two of these examples as well. So take this example as well as this example over here. Okay, and see what happens.
Okay.
Okay, run it many times. So the important thing is that you should repeat this multiple times. So you write this code. Yeah, you write this code, and then run it maybe 10 times or 20 times or something. Ideally, you would have to run it for a very large number of times, but every time you run, this sequence will look different. But then this sequence will behave more deterministically because after a certain point, all the numbers will be small.
Sir, like if we are doing for the above thing, like the given third example,
Yep.
then we have to take all our independent random variables, right? Like here,
Correct.
at least
Correct.
the converging point x is already defined, but the
It is
converging,
already defined. Correct.
but the converging thing also we have to take the random thing.
Correct. So another way of determining whether a sequence of random variables converges or not is to look at the difference between consecutive random variables, right? Or so in this case, also try to look at say x2 minus x1, x3 minus x2, x4 minus x3 and so on, and also maybe if you take n to be, let us say 100, n equal to 100, then maybe you try to print x1 minus x maybe 70, x2 minus x70 and so on. So x3 minus x70, so on. Okay, and see what happens. So in this case, in this particular example over here, you had to guess what the random variable x was. So in general, if you want to check whether a sequence converges almost surely or not, then one way to do it is to check for x, check what happens to x1 minus xm, x2 minus xm, and so on for really large m. So if this sequence converges almost surely, then this sequence should also converge to 0. Okay, and you'll see that try to do this. So try to print this for each of the above examples given here, right? So try to do it for this example, try to do it for this example, and also try to do it for this example. So you'll see that in the first, in this case, that sequence, the difference sequence, will converge to 0. But in these two examples, this will not always converge to 0. If you run the program multiple times, then there will be certain instances where this sequence does not converge to 0. So you will see some ones at some point later on for large enough n, and even in this example, the sequence will not converge to 0. All right. So this is. So sequence of this form is typically called a Cauchy sequence. Right? So basically the difference between terms. All right, and convergence happens if and only if this sequence converges to 0. All right.
Sir, can you provide any reference book on which, I mean, in which we can find such more solved problems? Because I've tried in populars and all, I couldn't find many examples.
Okay, so you can, I'm not sure if, well, examples are a little harder to find. Typically, in most cases, most books will just talk about
Convergence in
yeah, just
different.
convergence definitions and then
Yes.
theorems. Maybe one place to look is the books by William Feller.
Okay.
There are two books. There's a volume 1 and volume 2. I think the title of the book is just probability.
Okay.
But just look for this author. There are two books. I'm not sure which book deals with convergence. Probably volume 2. You can just see.
Okay.
This book, this is a very nice set of books, particularly because it has a huge number of examples. Hopefully, this might have some more.
Sure, sure, sir. Because I have seen, I mean, probability, as we have talked about three different convergence things, so there are
Yes.
many more actually. Like when I went.
Yeah, there are many more. This convergence in expectation, convergence in moments, and so on. But generally these are what are probably most relevant to us.
Okay, okay. Thank you, sir.
So and in a course in probability you would have seen all these three notions of convergence. Convergence almost surely, because the strong law of large numbers is basically a statement about almost sure convergence. The weak law of large numbers is a statement about convergence in probability, and the central limit theorem is a statement about convergence in distribution. So you would have seen three statements corresponding to these three notions of convergence, and they are different. So just recognizing and understanding the fact that these three are different, that one is weaker than the other, that is what is most important.
Okay, sir. Thank you, sir.
All right. Any other questions? All right. Okay, so in the last class we talked about degraded channels, and when you say that one channel is degraded with respect to the other, whether two BSCs are degraded with respect to one another, and so on. Right. So with that we wrap up our sort of very basics of probability, information theory, and sequences. And now we'll start talking about actual information theory. So again, this is a topic that you would have seen in a previous course, but we're going to do this in a much higher level of detail. So recall that the channel coding theorem, that both the source coding theorem and the channel coding theorem had two parts. There was an achievability which says that you can construct codes, you can construct compressors, you can construct channel codes which achieve a certain bound. That is, you can drive the probability of error down to 0, and also you can have a rate close to either the entropy or the capacity, depending on which problem you're looking at. But there's also a converse part to both these theorems. And it says that if you try to operate, say, above the fundamental limit or below the fundamental limit, that is, if you try to compress the source at a rate below the entropy, or you try to communicate at a rate above the channel capacity, then the probability of error will not go down to 0. It will be bounded away from 0. Okay, and that is what we'll try to prove now. And the main tool for proving almost all theorems, or almost all kinds of converse results in information theory is this very useful inequality called Fano's inequality. And it arises in a number of applications, not just in source and channel coding. Even when you talk about statistical inference, when you talk about problems in estimation or detection, Fano's inequality is a very, very powerful tool. Right, and you use Fano's inequality to typically get a lower bound on the probability of error. It doesn't give you the best sort of bound on the probability of error, but whenever you want to show that something is impossible to do, that the probability of error is bounded away from 0, Fano's inequality is a very powerful tool. All right. So what does the inequality say? The inequality says that if you have two random variables, okay, so you have m, which is the random variable of interest. So this is the quantity that you're interested in, and let us say that you have an estimate of the random variable using whatever mechanism. It doesn't matter how you get m hat. Maybe m hat is, so m is the true message, and m hat is the message you obtain by after decoding at the receiver, or it could be an estimation problem where you're interested in m, but then you observe something else and then you make an estimate based on what you see, and you call this m hat. That it doesn't matter how they're jointly distributed or how you get m hat from m, but as long as you have two random variables m and m hat, which are jointly distributed over the same alphabet, and let us define the probability of error as the probability that m is not equal to m hat. So the probability that that your estimate is different from the actual random variable, then you can get a lower bound on the probability of error in terms of the conditional entropy. So the entropy of m given m hat is less than or equal to the binary entropy of PE, the probability of error, plus the probability of error times log of the cardinality of the set from where m and m hat are coming from. Okay, so even before we prove this, let's try to inspect this and see what is happening, to at least get a qualitative understanding of what this is saying. So let us say that so you have m hat and m. So if m hat is equal to m, then what can you say about h of m given m hat?
H of m?
If m is equal to m hat,
Sir, entropy will be zero.
it will be 0, right?
0 it will.
Yes.
So if m is equal to m hat with probability 1, then h of m given m hat, this will be equal to 0, right? And in that case, of course, the probability of error is also equal to 0. So that's indeed what we would expect, because if PE equal to 0, then this quantity is 0. The second term is also equal to 0. So definitely that is what we would expect. And what if m is independent of m hat? M hat independent, then what can you say about h of m given m hat?
So that will be maximum.
H of
Correct.
m.
It will be maximum and it will be equal to h of m. Right. So the maximum is achieved when m and m hat are independent, and that is indeed what you would expect. That in this case, the probability of error would also be the maximum, right? Because m is totally independent of m hat, so the probability of error would also be large. So in some sense, if the uncertainty about m, given that you've seen m hat is large, then the probability of error is also large, right? And that is what one would intuitively expect. And that is precisely what Fano's inequality is saying, that if there is a lot of residual uncertainty in M given M hat, given your estimate, then the probability of error will also be large. All right. So let's try to prove this inequality. Okay, and it's a very simple proof. So you start with by defining a random variable E, which is basically the error random variable. So the error random variable is 1 if M hat is not equal to M, and 0 if M hat is equal to M. Right? Because ultimately we want to get this probability of error somehow. Right, and basically this error random variable tells us whether the estimate is erroneous or the estimate is equal to the actual M. Right. So what is h of E equal to? So in terms of PE, what is h of P equal to?
H2 of P.
Exactly. So it's equal to, so E equal to 1 when there is an error. So E is basically a binary random variable. The probability that E equal to 1 is basically equal to, it's the probability of error, right? And PE of 0 is basically 1 minus PE. The PE is what we have defined over here, the probability that M is not equal to M hat. So the entropy of E is basically the binary entropy of PE. All right. Now we want this particular quantity over here. So let's start by looking at h of M E given M hat. Okay. So we'll start with this quantity and we'll try to expand it using the chain rule. So I want this particular quantity, h of M given M hat. So I'll write h of M given E M hat as h of M given M hat plus what is it? What's the next term going to be?
H of E.
E given M comma M hat.
Correct. So E given M comma M hat. So basically the uncertainty in M given M hat is equal to, so h of M E given M hat will be h of M given M hat plus h of E given M and M hat. Right? So that's what the chain rule tells us. Okay, so the first term is easy to bound. So let's keep it as it is. But this is also equal to h of M. Okay, so let me maybe write it over here. So this is one way of expanding h of M E given M hat. Another way of expanding this is to use h of E given M hat plus h of M given E comma M hat. Right? So these are two different ways of expanding the same term using the chain rule. Okay. Now let's see, what do we want? We want a lower bound on, an upper bound on h of M given M hat. So let's see what h of M given M hat is. So from this, h of M given M hat is equal to h of E given M hat plus h of M given E and M hat minus h of E given m hat. Okay. Now let's look at this. So we want to derive this particular expression, and let's see. We somehow want to show that this is upper bounded by this. This is upper bounded by this, and we want to somehow get rid of this. So let's start with the rightmost quantity. So what can you say about this? I claim that this is equal to h of E given m hat plus h of m given E comma m hat. Why is this true? So why is this inequality true?
Sir, for equality, we are subtracting something and we are eliminating, we are starting this h of E
Okay.
given m.
But what property am I using over here to get this inequality? So
Can we
if I
say
have
union bound?
not the union bound, so I have three numbers, right? So A, B, and C, and you have A plus B minus C, and I'm saying that A plus B minus C is less than or equal to A plus B. So what property about C am I using over here?
So last term shouldn't be 0 because given aim and aim at we can deterministically calculate what is E is.
Correct. So given m and m hat, you know exactly what E is, because E is a function of m and m hat, right? So in fact, this is not just an inequality, this is an equality. Right? Because E is a function of m and m hat, and since E is a function of m and m hat, the entropy of E given m hat is equal to 0. Right? Okay. So, all right. So now I'm going to write this as less than or equal to h of E plus h of m given E comma m hat. Why is this true?
Because sir, making some condition of entropy, it will be entropy.
Correct. So conditioning can only reduce entropy. So h of E given m hat can only be less than or equal to h of E. All right. So here E. So the first step, I use the property that E is a function of m and m hat. In the second step, I'm using the fact that conditioning reduces entropy. Right? So this is less than or equal to h of E plus h of m given E and m hat. Okay, fine. So, all right. So this is equal to. So h of E is basically, as we've noted before, this is h of PE. So we already have one term ready over here. So h of PE. Okay. So plus. Now I want to see what happens to the second term. So to do this, I'll split this into two parts. So h of m given m hat. Now E can take two values. E can either be 0 or it can be equal to 1. Right? So I'll write this as h of m given m hat and E equal to 0 times the probability that E equal to 0 plus h of m given m hat and E equal to 1 and times the probability that E equal to 1. Okay. So given that E is equal to 0, what can you say about H of M given M hat E equal to 0? So if E equal to 0, then what does that say about M and M hat?
They
M
are
and
That
M
will be
hat
zero.
equal.
equal.
Correct. So when E equal to 0, it means that there is no error and M is equal to M hat. So given M hat, you know exactly what M
M
is.
equal to M hat.
Correct. It's M equal to M hat with probability 1. So this quantity, this is equal to 0. Right? So we are left with just one term.
So the second term will be 0.
The second term is not 0, right? H of M given M hat E equal to 1 times PE of 1 is just the probability of error. So let's look at the second term. So the second term is E equal to 1. So M is not equal to M hat, right? So among whatever cardinality of M different values, you know what M hat is. You know what M hat is, and you know that M is not equal to M hat, right? So it means that M could be any of a number of choices. All you know that it is not equal to M hat. So for example, when capital M, so suppose that M and M hat come from the set 1, 2, 3 up to 10. If M hat is equal to 3, M hat equal to 3 and E equal to 1, then you know that M is not equal to 3, but it could be 1, it could be 2, it could be 4, 5, 6, all the way up to 10. Or you know that it is not equal to 3. Right? So there is still a lot of uncertainty in M given M hat when E equal to 1. Right? But now we are going to use another property. I'm say that this is equal to PE times H of M. Why is that true?
Because M and M hat are M is independent then of M hat because P of
No,
A.
M is not necessarily independent, right? It is dependent on M hat because you know that it is not equal to M hat, right? But this just comes from the fact that conditioning can only reduce entropy, right? I just want an upper bound.
Yes. Okay, sir.
Right? So I just want an upper bound. I don't need to know what exactly it is equal to. I know that this is less than or equal to H of M, and that is good enough. Right? But I'm going to do something even more loose. So I'm going to say that, so what is an upper bound on H of M? What is the maximum value that H of M can take?
It's like log of
Log
cardinality of
to
M.
cardinality of that M hat.
Correct. So it is log cardinality of M. Right? And with this we just basically get Fano's inequality. That's it. All right. So again, it's fairly simple. Just try to work it out once again later. Okay. So we are going to use Fano's inequality to prove the converse of the channel coding theorem. All right, and let's see. So once again, just to recall, the channel coding problem is the following: you have a sequence of k IID uniform random bits, the message sequence. So you want to send kn message bits through a noisy channel, a discrete memoryless channel with transition probabilities py given x, and you want to know what is the best performance that an encoder and decoder can have. So what is the best pair of encoder and decoder that you can construct? Right? So you map the kn bits into a sequence or a code word of length n and transmit these n symbols across the channel one after the other each of these symbols is corrupted by the channel according to this distribution Py given X, and you observe a Yn at the receiver, and the receiver tries to decode Yn to get an estimate of the message bits. Right? And we want to know what is the maximum rate at which you can transmit, what is the maximum k by n that you can achieve while simultaneously ensuring that the probability of error is vanishing. Okay, so the converse to the channel coding theorem says that no matter how you construct your encoder and decoder, if you try to operate at a rate above c, so suppose that you fix an asymptotic rate equal to c plus some epsilon, where epsilon is some small quantity greater than 0, then asymptotically the probability of error will be large. It will be greater than or equal to epsilon. Okay, and we'll try to prove this using Fano's inequality and also a very nice property of the mutual information. So basically, if you take any random variable xn, if you obtain yn by passing xn through a DMC, then the mutual information between xn and yn is always going to be less than or equal to the sum of the mutual informations between xi and yi. So these two tools will be used to prove the converse of the channel coding theorem. All right, and so but one thing to note is that this statement over here. So this statement over here is not true for any joint distribution Pxn yn. So for example, if this channel were not memoryless, if Pxn yn, so here we're using the fact that Pyn given xn is equal to the product I going from 1 through n of Pyi given xi. All right. So if this statement is not true, if the channel is not memoryless, then this inequality does not hold. Okay, so we're very crucially using the fact that the transmission is happening through a discrete memoryless channel, and only in that case this particular result holds. So this is sometimes called the subadditivity property. The subadditivity, or sometimes called the tensorization property of mutual information. All right, and so with this subadditivity property and Fano's inequality, we are going to prove the channel coding theorem, or the converse of the channel coding theorem. And this holds. We'll use a similar property whenever we talk about multiple access channels or point-to-point channels or even broadcast channels. Right? Because this sort of subadditivity or tensorization property holds in that case as well. So we'll try to use a similar result. All right. So any questions so far? Okay, so if not, maybe this is a good point to stop, since we won't be able to complete any of these statements today. So from the next class onwards, we'll probably try to speed up a little because we're a little lagging behind. I'll also give some of the sub problems as homework exercises, so that's also a good way to test whether you can use the information theoretic properties well enough, but we can also always discuss this in class later. Right, so any questions? All right, so if not, then we meet in the next class, which is tomorrow.